and Jonas Top is from Facebook Research, and Jia Bin Huang was from National Tsinghua University. So we contributed very little to the author, to their contribution. So let us proceed now. So a spoiler. So what I'm going to do is the left one is a static image. This is not a layer depth image. So what is a layer depth image? Layer depth image is like with certain amount of color intensity value, the image will also have a depth value. But we are using just a camera, means with only by using my phone, and I have taken this photo with a single camera, and using that I will ask it from model, and it will generate something like this. So this is a little bit free. If you can see, perceive it quite well. So this will be the work. So it contains most of the work from GAN, UNET, and other latest technologies that were developed by deep learning researchers. So next, we will see the table of contents, how we are going to present this paper. So firstly, we will talk about introduction, then related works, then materials and methods, then experimental results. Then we will talk more about our custom inputs and some of the drawbacks of this method. So for drawbacks, we will refer to the original papers, which were which technologies the inpainting paper was using. So it is kind of a dependency problem there. So we will also cover those, and we will tell about the conclusions and references. So firstly, introduction. So overview. Okay, so conversion, we will convert a single RGB image to its 3D depth invariant. So what is RGB image? So RGB image is anything like anything we capture from phones, any mobile phones. Low quality image can also be RGB, and the better variant, which gave better result for their for the paper, original paper, uses two camera two camera lenses. So that gives kind of a depth value to the RGB image. So it also needed high resolution and dual camera to capture the depth map. So how can we cover this? How can we cover this 3D inpainting? So we will, since we are using a single 2D image, so we will use parallax. So parallax means we are separating the image into multiple layers and moving one layer a little bit slower than the other. Okay, so the farther layer which are lying at the back will be more slowest movement, and the layers which are in the front will be a very fast movement, So we will use parallax to create fake 3D environment from single 2D image. So this parallax effects creates a kind of hallucinated effect. So this will create a immersion in 3D. And for all those parts of the image which are occluded, because we are dividing an image into layers, so that we have to do inpainting method, which is kind of a GAN method, generative adversarial neural network method, with some other trends such as UNET and segmentation. So we will cover those in the later slides. But this paper is not just a single paper. This is composed of about 40 papers, which are all state of the art. So we will talk about all of them, I mean some of them, not all of them, but we will give some hand wavy and overall arguments of how they can improve, or some overview of their methods. So we are using the learning-based inpainting model, which synthesizes new local color and depth content into occluded region in a spatial context-aware manner. So in a GAN, we generally use different kinds of generative model for creation of new content. So we are using this. Now the photos can be rendered using 3D graphics engine, which is portable. So a good and computationally efficient method will be able to handle these photographs in some low powered ARM processor or anything like mobile devices like Snapdragon, or mobile devices also. So this can be embedded there. So this won't be a problem, much problem in integrating this algorithm into Android devices. So why do we need 3D photography? So this is kind of silly. 3D photography is a fascinating way to record and reproduce visual perception. So for creating new means for seeing the old memories in a more immersive way, so we can create 3D photography. Just like color pictures are superior to black and white photos. So in that way, we can say that we need 3D photography. So extension of 3D photography can create virtual reality. So Pokemon Go is a kind of a simple version of a virtual reality. So there will be more development in this field. This is kind of a recent field. So yeah, 3D photography can be used on virtual reality as well. So normal flat surfaces, when displayed with parallax, causes 3D effects, which I told that we will divide an image into layers, and after that we will create segment the layers and create parallax from those layers. So we will come to it in the coming slides. So classic techniques to capture 3D images requires two-match camera. So we have all read about stereo visions, 3D reconstructions, all those stuffs. So they use two-match cameras and with high precision camera, like all those epipolar geometry. We saw that we need some fundamental matrix, all those hyperparameters tuning and all those stuffs. But we will, for this paper, this is kind of the state of the art, and it is presented in 2020. So this uses only a single image, and it is quite good. So we can use graphics interchange formats like GIF, which are very short video formats, to provide a standard experience with very less computation. Okay. So next we will see the recent novel methods. So these are the recent novel methods that are done by different organizations. Like this is done by one university from California, and this is also done by this team only, a YouTube version of this. But we can see that this thing, when they are using this, so we are firstly creating a context. So this is the context. So this will be in the first layer of the parallax. So this will move a different speed, and the background will move at a different speed. So they are creating a hole. So this is a drawback of this method. Okay, so this is one of the naive method, and this is also a drawback of another method, which are creating stretching effects. So this team only created this. I have read their paper. So these were about in 2018 or so. So not so much old. And this is Facebook's photography, 3D photography. And what we can see is this kind of have a ghost effect still. So this is also kind of a drawback. And they're all using the inpainting method. And inpainting refers to kind of a generative adversarial neural network method for generation of new content in this occluded region. So what their result does, is our result which we are presenting, is we will fill this gap with more suitable content. Like we are not taking the posterior probability of the surrounding region and calculating this. So we are doing something like GAN with near depth sensing. So this is kind of a we are taking something from the surroundings, but those are not affecting too much. So we'll come to it. Don't worry about this. So Facebook's 3D photo uses layer depth image representation. This can also be converted to lightweight mesh representation for rendering. Like they are also rendering it in Facebook Lite, which is very computationally efficient. And color and depth from occlusion is synthesized by heuristic, which I told is it is synthesized by like posterior probability calculation and all those stuffs. Means just statistical analysis. Given that the surrounding pixel are very similar to the occluded region pixel. Okay, so what are the shortcomings of this method is it is unable to extrapolate structures and produce overly smooth results like ghosting effects here, which I told you. And several learning-based methods use similar multi-layer representation. So they are using multi-layer representation using LDI representation, layer depth image, which are having a depth value for each pixel. So this is it. So other methods use fixed number of predefined layers for each pixel. So other methods like this, suppose this one, let's say, it will use 2 layers. So this is creating the posterior layer and this is creating the background layer. So this will create a parallax, this will move, and this will be the another layer. So this is constrained to 2 layers. But our method, this method, will have multiple layers using context-aware layered inpainting methods. So it will have some attention mechanism which are used in GAN to create context-aware depth sensing. Okay. So the naive methods are very problematic because abrupt change of depth discontinuities can cause tremendous effects in picture disocclusion. Okay, so what may happen that this is a very clear image, not talking about this image. It may even happen that when we are capturing some image in a low quality camera, it may even happen that the depths are not perceived quite well. Means these edges will have very smoothing effect. So in that case, we will use something like correlation filtering and sharpening filter for detecting the edges for determining the layers. Okay. So earlier methods can cause holes, which I told, and even uneven stretching and unpleasant results. So this method, which we will present, surpasses all the methods. So now I'm going to give you a brief overview of the algorithm. So we will break the picture into sub-problems to iteratively solve in painting. So we are breaking the picture, suppose this picture, into sub-problems. So this is not creating a fixed layer. We will suppose this will have a different layer, this will have a different layer, this will have a different layer, this will have a different layer. So this will create an immersive effect and a good 3D approximation of the method. So use of convolutional neural networks makes breaking results and produces easier result, much easier for computation. Okay, so since we are dividing into sub-problems, convolution happens to be faster in those areas and they are providing a good result. So spatially adaptive context region to context for in-painting model. So we are spatially adapting the context region. So we are not fixing any depth or anything. And after the synthesis of the context region, we will fuse back the images to LDI, means layer depth image. So this provides some good results for synthesized textures in occluded regions. Okay. The algorithm determines the number of layers by adapting to the input images. So this is an iterative algorithm, just like grab cut or something. So all those stuffs. And this heuristically solves those context-aware depths and helps to create a perceived notion of the 3D environment in a more smoothie environment. Okay. So all these factors led to the creation of automated layer extraction algorithm for better results from the current competitors. So we will talk about the related works which are done recently. This is not older than 5 years. So few methods to create 3D photographics are light fills. So light fills is what is does is we will take a single image. No, we will take 2 images with different light intensity. Just like focusing and defocusing can cause some depth estimation of depth values. So light fills can also be can also enable photorealistic view, but many photos are required for good results. So multi-plane geometry uses multi-layers of RGB alpha images at fixed depth, which captures semi-reflective and transparent surfaces. So since we are using since we are using multiple images, so that will give a good heuristic to how to invent the model and how to create a 3D photograph using a 3D immersion using that. So layer depth images. Earlier methods uses fixed number of layers, as I told. So this work uses auto capture of any number of layers, preserving depth discontinuities. So this is a heuristical methods which have an iterative algorithm. So I will come into that in the next slides. So this also can be converted to textured maps for efficient rendering and conversion into GIFs or VLC or MP3 or any formats like video formats. Okay. So next comes image-based rendering.
So Jimud, one
So
question.
light
So
fills. Light
Jimud,
fills enables photo. Yeah. Yeah.
one question.
Yeah.
So do you have that some example of the reflective and the transparent surfaces later? That will be
Reflective and
really, I think,
transparent.
valuable.
No, I don't have actually. No, 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 no.
Okay, okay. But did in the paper, did they
Yeah.
mention anything about that? Like some
No, no,
example?
no, 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 no. They didn't mention anything about
Okay,
that.
okay.
I thought of including that, but it will be too long actually. It will be covering multiple papers, so it will
No
be
problem, no
time
problem.
consuming.
Yes, continue. And time should not
So
be in a worry. You can
wait a
just
second. Let
take
me.
your time. If it will take more than 40 minutes, that's fine too.
Yeah.
Okay.
Yeah. Yeah. Okay. So light fills image-based rendering. So light fills enable photorealistic view, but requires many photos. So then we have 3D stereo algorithms, which we have studied, like in the photosynth, which I have also shared one video in the Google Classroom, if you remember. So those algorithms uses multiple images. So for multiple images, we can construct something like point cloud of the 3D model. So that will be more of an accurate model, like a leader thing, LIDAR, leader. So SLAM method, leader method, then 3D reconstruction, all these kind of are similar research topics. But we will go some like basic overview over this. Okay. So recent advances of these types of works include learning-based blending, soft 3D reconstruction. Now, what is soft 3D reconstruction? Soft 3D reconstruction was first invented by Facebook group. I have seen their paper, and this is also kind of similar to this the example which I showed, that ghost effect of Facebook. Like they are creating a kind of occluded scenes are using the posterior probability to develop the layer depth image with some uh, surrounding pixels and all those things. So those are learning based reconstruction and soft 3D reconstruction. This soft 3D reconstruction is kind of just a minor version of which we are going to present. Okay, so our version is superior than soft 3D reconstruction. So handling reflection. So recent so multi-view stereo algorithms can handle reflection, since we are using different kind of different angles of images. uh, huh Hello, Raj, are you asking something?
No, I think Devadri's mic was on. Devadri, you have a question?
Huh, Raj, I'm continue.
Maharaj, you can mute him.
Continue, continue. Yes.
Yeah. So learning based. So I have talked about 3D reconstruction, 3D reconstruction, soft 3D reconstruction, hiding reflections, and reconstructing mirror and glass surfaces. So soft 3D reconstruction can also reconstruct some certain reflective surfaces, because they are using multiple images, and we can average them out, and we can create a smoothing effect, and we can create a perceivable notion of 3D geometry. Okay. So we will. So we are talking about learning-based view synthesis. So CNN-based methods have been applied to synthesize novel views from sparse light field data. So what is meant by sparse light field data is we are not having so much light in that means so much intensity or so much light or so much posterior probability to give a general overview of where to synthesize what in painting models to use. Okay. So CNN-based methods are superior because they are using deep learning and all those stuffs, and they are kind of learning an abstract notion of a human brain, so they can perceive better than almost every other traditional algorithms. So CNN based methods are very useful for synthesizing novel views. So several methods have been proposed, but they often focus on a single specific image, like synthesizing synthetic 3D scene or object, or specific view hallucination, assuming specified palette scenes. So what it is telling is several new methods which have been proposed, means earlier to this methods 2020's paper, they are just talking about a single specific constrained image. So suppose of a image is containing a foreground of a child, so it will only focus on the child, not on all the layer depth image and synthesized region. Okay, so they are very constrained to a environment, certain environment. So what our method does is it requires a running of a forward pass of the pre-trained network to synthesize the image of a given viewpoint, which is computationally expensive. So recent methods also uses this, which uses forward pass, but our method uses a variant of UNet, which have some constraint in the convolution, means they are skipping some convolution. So we will come to that later. So forward pass means we are also using some kind of deconvolution, just like UNet. So forward pass is just forward pass, and forward pass have a very computationally efficient in some cases when the model is quite small. So our method can be embedded in ARM processor or mobile devices too. So now we will talk about some image inpainting. So image inpainting refers to the filling of missing regions of image with possible content. Excuse me. So what is inpainting actually required for? So as Anil suggested out earlier in my discussion with him, so Anil said that inpainting are used to remove watermarks. So to remove watermarks, inpaintings are used to fill certain vacant spaces or holes in an image. We can use inpainting. So general inpainting, which are very naive, refers to the addition of patches of known regions to unknown regions by belief propagation algorithm, like Markov models or something. There is also one like deep belief networks. So it is that is a paper by Alex Krivitsky, very old, and that was a improvement of that LeanNet, as we all know. But also RBM, that is restricted Boltzmann's machine, have also sufficient contribution in the development of CNNs, because RBMs are kind of classical statistical method. It's not kind of deep learning, I would say, rather, because RBM uses Bayesian distribution and probabilities to help to give a kind of generalize well on the unseen data. Okay, so our procedure for inpainting is as follows. We apply inpainting locally around each depth discontinuity with adaptive hole and context region. So as I said before, that our method can synthesize different layers by proposing a certain area. Okay, so earlier methods, as I said, that they are using a fixed number of layers, say suppose 3 or 2 layers, but our method can iteratively count upon how many layers to give a immersive experience in creation of a 3D content. So we implement the depth values and discontinuities in the missing regions. Excuse me. So depth inputting refers to filling of depth missing values in general. When commodity grade dual cameras fail, so depth inpainting generally happens to be a good result when we don't have dual cameras. Means suppose everybody is not having Apple phones. Okay, so Apple dual cameras phones for good result, or high resolution DSLR dual cameras or anything. So in that case, we can approximate certain 3D content using a single camera. So we can also use image editing task, like in Adobe or all those copyrighted software. They are kind of using this inpainting method in general now, and they are transforming their methods from classical machine learning to deep learning methods. So our algorithm inpaints the depth of visible surfaces. So firstly, I will come to it in the next forthcoming slides. So we will talk about how the algorithm synthesize the depths and model and the network's inpaints models. Okay, so it mainly focus on recovering the depth of occluded or hidden surfaces. Yeah. So when we are inpainting, we are covering we are segmenting an image into multiple layers. Yeah. So when we are separating an image into multiple layers and we are creating a parallax effect, so parallax effect will create a hovering effect or anything movement. So it may happen that we will have some holes in those inpainting models. So in that case, what we will do is we will recover the depth of the hidden surfaces, and we will inpaint the background with respect to the foreground. So we will come to it. And so CNN based single depth estimation is what we are going to talk about next. Is as I said, it gave a very promising result in creating depth from single image, because CNN we are using by partitioning images and then applying the CNN on that. So due to the scarcity of available data set, means available label data set, which have a corresponding depth value and a corresponding image. So stereo images are very hard to create, because we will see that we are limited to a camera movement, and we need high precision image to create label data set for stereo images. So in that case, we don't have so much of available data set. So in that case, this focuses on a specific visual domains such as indoor scenes or street views. So current data set focuses on a specific visual domains such as indoor scenes or street views. Excuse me. So the accuracy of this algorithm is not yet competitive to multi-view stereo algorithms. Since we are not having so many images, so it is quite challenging nowadays to have a competitive accuracy of these algorithms to the multi-view stereo algorithms. So the field is quite promising, because many data sets will be available in the future. So we are having 3D movies, so we can use those as a data set, custom data set, using partitioning the movies into frames and all those stuffs. And we will get a whole lot of an image for a particular data set. So we can use 3D movies for synthesizing data, and this can foster new research in the coming future. So we can also use synthetic data. Like suppose a good example is I have seen in YouTube that a guy named Harrison Kinsley uses Grand Theft Auto. Many of us has played Grand Theft Auto, GTA 5 and all those stuff. So what they're doing is, see, when we are using a synthetic data set, there will be some planning involved, and in a real world data set, there will be some problems when we are converting a synthesized model to a real world model. But in case of a synthetic model, we don't have any cost of damage. So if you are using a car, and in the real world, and if you are using a reinforcement learning or something like that, and in reinforcement learning, they are constantly having failures. So if we crash a car, so it will be a huge problem. So in that case, what they're doing is they're creating a synthesized environment, mainly in Unity 3D and all those game engines. And using that, they're converting, they're training the model there. And because any damage in their synthesized model will not have hamper the actual model. So cost is very less, and using that, they're converting into real world models and applying it into a car with some constant, because real world friction will be different, real world handling of cars will be different, frictions, all the stuff comes into play, drift, all those stuffs are coming into play. So synthetic data are posing to be a good innovation in creating 3D depth images. So we are obtaining a depth estimation from a single image using a pre-trained model. Okay, so since we are using a single image, so we will use some pre-trained model. So removing the dependencies such as multiple images, in the case of stereo, this method is applicable to a variety of images. So what we are trying to achieve here is earlier methods, maximum of the earlier methods uses dual camera and all those like constrained camera movement, specific, very accurate movement, all the stuff they are just having to we can just sacrifice those methods, and we are just focusing on a single image, so that we can use this in day-to-day lives where such precision is not always available. So now we will talk about materials and methods, means how this stuff was done, and all those related papers, all those dependencies which this paper was using. So layer depth image, the method takes a single RGB image that is aligned depth and color image and generates a layer depth image, which is independent color of the depth of occluded parts. So LDI image have four connected components, just like when we are doing a seed fill, we are means in graphics algorithm, when we are doing a seed fill, we are constraining ourselves to the current pixel and all those 8 neighboring pixel. But here we are constraining to four connected image and four connected pixel of the image. Okay. So it can hold any number of pixels from 0 to many in every position of the pixel lattice. So what is how is LDI different from a single RGB image? RGB image can only have in a single pixel it can have 3 values, that is 4 values if you are considering the alpha channel as well. But in LDI they are having a depth values. So depth with each layer of the image corresponding to the surrounding pixels. So this is a little bit a complicated topic, not so complicated, but we can visualize this in the forthcoming slides. We will see go through it. So, and in LDI, pixel does not have neighbors across depth discontinuities. So in general layer image, we are having depth discontinuities, but in when we are considering LDI, we do not have neighbors across depth discontinuity. So discontinuities will not affect the overall accuracy of the LDI extraction algorithms. Okay, so LDI, each pixel of LDI stores color and depth values. They are used in 3D photographics because they can naturally handle any number of layers. So LDI is not so old. It is currently available tool for creating 3D photographs because in a certain photographs there may be different contexts, and for different contexts we are having different layers. For different layers we are creating different angles of stereos. So in those cases we will see in the forthcoming slides how it is done. So uh, LDIs are generally sparse because they are only having constraining to 4 different connected components on a single pixel. And for since it is sparse, we can convert it into lightweight texture mesh for fast 3D rendering. And also we can also use some OpenGL. So I think as far as I remember, Windows uses DirectX, then OpenGL is a standard format, and a lighter version for web is WebGL. So these are all 3D rendering engines, and if you are doing game development on all those stuff, you have to code this from scratch. So means there are certain parameters. So I'm not going deeper into those topics. So we can get a general idea by 3D engines and all those stuff. So what I will discuss in this method slide is, firstly we will do the image processing stuffs, then we will synthesize the contexts of certain layered images, then we will do the we will see the context our layer depth inpainting model, multi-layer inpainting for different layers, and how we generated the training data. And at last we will convert the 3D textured mesh to video. So when we are converting an image, or as Tamal Maharaj also have given one assignment, and I don't remember how many of you have done it, but yeah, we can use Mesh Lab to convert this 3D textured mesh and visualize it in real time. So we will also go on those stuffs also. So image pre-processing. Firstly, we need to pre-process the data as usual, as it is norm of a deep learning algorithm. So we are giving a single RGB image, but it also works for fine for single RGB image also. We will see it. And we normalize the depth channel by mapping the mean and max disparity values. So it is necessary to normalize any values when we are passing to deep learning, because we have heard about the exploding weights and all the stuffs in machine learning class. So I'm not going deeper into those. So just remember that we need to normalize for faster results and accurate results. So we are scaling those image channels. So we lift the image to layer depth image by creation of a single layer everywhere and connecting each pixel to 4 cardinal neighbors. So here we are converting the single LDI or any image, single RGB image, to a single layer LDI image. So we are just transforming it or converting it to 4 connected sparse component which we have seen before in the before slide. So we are just transforming that. So we need to find the depth discontinuities since we need to implement the existing content. Yeah, because but we need to find the depth discontinuities since uh, for the creation of parallax, the background image should be painted more than the foreground image. So in that case, we need to create the discontinuities. We need to know the discontinuities and where to cut, where to merge, where to paint, and all those stuff. So we sharpen for this. So when we are taking a single image using a suppose a normal camera or suppose a normal phone camera. So what we are doing is uh, we are sharpening because it might happen that the uh, on a single image when we are taking it in a single camera, the layers are becoming smooth and we are not able to distinguish the one layer from itself. So we need to sharpen it with a median filter. Okay, so using a bilateral median filter, which is a non-linear filter, and edge preserving filter, we can refer to Wikipedia for more. So it is 7x7 window and sigma of spatial standard sigma of spatial is 4.0, sigma of intensity is 0.5. So these are hyperparameters of the bilateral median filter. So just for the information, this is not so much important. And after this sharpening of the depth map, we find discontinuities by thresholding the disparity difference between neighboring pixels. So we can see here. So this is suppose an image taken by a normal camera. Okay. So here we can see the raw image and have this smoothing effect. So in that case, we need to apply a median filter to kind of threshold it to separate the background from the foreground layer. Okay. So we are using the isolated speckles as shown in figure 2E. So after the thresholding, we will get something like this, just like what we have saw in corner detection, canny edge corner detection. So after that, this thing we will also, this is kind of analogous to that because the GAN which they are using, I have read a paper, so they are also using a edge. They are taking the posterior probability using the edge map from canny edge detector algorithm. So all those methods are fostering this 3D inpainting method. So this can be cleaned up using connected component analysis to merge adjacent discontinuities into a collection of linked depth edges. So after this, we will link those edges and we will create a layered image. So to avoid merging edges at junction, we separate the based on local connectivity of LDI. And finally, we remove the short segments which are less than 10 pixels, include both isolated and dangling modes. So suppose, let us consider this pixel, this part of the window. So suppose this is a 7x7 window. So we are seeing that there is a merging effect here. So in this case, it will be difficult for the algorithm to determine which levels we can apply the algorithm for the inpainting algorithm. So here we will remove this thing by applying the LDI components. So we are removing this and we are continuing this this depth map. Okay. So the final edges are shown in 2F by the application of inpainting algorithm. So now this is the LDI. So how it is happening? So these are suppose this is we are taking the parallax. So for parallax we will have different layers. So suppose this is one layer and this is one layer, and suppose there is one edge here. Okay. So it may even happen that the edge is very smooth. So the slope will be more. And what we need to do is we need to split this edge. So we will create an inpainting algorithm here on the below edge, which is in the background. So here we are using the inpainting on the red portion And here we are using the context aware synthesis region. And after that, we have made two layers using the LDI. So this portion is having the LDI, and this portion is having the initial LDI. Now, what we can do is we can move this and create a immersive experience. So I have talked over. I have given an overview of this. So, inpainting algorithms operate at one of the previously computed depth edges at a time, and one of these edges is shown here. And we need to synthesize new colors for this background content, which is occluded adjacent occluded region. So, this is the occluded region. Wait a second. Yeah. So we are starting by after this method we are going this and just splitting this so that we can create a context aware synthesis of the two layers, and we call this silhouette pixels because these pixels won't be affecting much in the synthesis. We will only focus on this, the background region. And background silhouette, which is given by red, needs indenting by extending the surrounding to occupied regions. So we start by generating a synthesis region, a contiguous region of new pixels, and these are essentially just 2D pixel coordinates at this point. So these are 2D pixels, not 3D pixels. We initialize the color and depth values in the synthesis region using a simple iterative flood fill-like algorithm. So in this portion, we will create a flood fill-like algorithm just like computer graphics, and by the application of that, we can create a context-aware synthesis. So we will do this for 40 iteration, and we will convert this. So how we are performing the context and synthesis region for this part. So for each iteration, we expand the context and synthesis region alternatively, and thus a pixel only belongs to either one of these two regions. So either a pixel belongs to this layer or this layer. Okay, so we will do this iteratively. So we will create some layers to give get a idea of how many layers can be possible. So in additional, we do not step back across silhouette, so we synthesis region remains strictly in the occluded part of the image. So this is the context region blue, and synthesis regions are in red. So this will be synthesized and this will be context. So the foreground will move, and this will also have to be inpainted for a better immersion. So many technologies uses this inpainting to fill holes in images based on known surrounding context, but in our method we may not find any known content. Yeah. So as I said, the previous methods which are using that Markov belief networks and all the stuffs, they are using using an approximation that the prior regions, the surrounding regions, will have a known content. But in our case, it may also happen that we don't have a known content. So we should only be constrained by surrounding pixel that is directly connected to it. Any foreground or background layer is entirely irrelevant for the synthesis unit and should not constrain or influence it in any way. So the previous LDI algorithms uses some posterior probability and surrounding regions to give a depth map, but our algorithm is superior in the sense that it doesn't get affected by the surrounding pixels. So we achieve this by explicitly defining a context region for synthesis. So inpainting method only considers this region and doesn't see any other part of the LDI. So the context region is generated using a similar flood fill right algorithm, which I have said before. So wait a second, let me drink some water. Yeah. So suppose we are giving this as a context region. Suppose we are we are assuming that in this picture we are having two images. So first is this foreground and this is the background. So we will have two layers for this. So this is the context region and the synthesis region. So in the context region, in the synthesis region, we will take the posterior and use the GAN method to have this synthesis region inpainted fully. For this region, for this we can apply a much angle to the parallax when we are happening to cover the parallax. Okay, so as the depth edges may not align well around occlusion boundary, we dilate the synthesis region by 5 pixels. So we can also dilate the synthesis region by fully context region, but we are just limiting it to 5 pixels for computational efficiencies and all the stuffs. And after that, we run this algorithm for 100 iterations. So there is one code available in Colab. They have open sourced it, and I have used that code for making some of my photographs in 3D. So they have used 100 iterations for any photographs and used some pretend models which were stored in .npz formats, not H5 formats. So NumPy is probably more efficient than H5, but we are not going into those details. So in practice, the silhouette pixel may not align well with the actual occluded boundaries due to imperfect depth estimations. So as I said, this may not be well occluded. This may not be well aligned with the occluded boundary. So in that case, we need to synthesize. So we dilate the synthesis region near the depth 5 by 5 pixels, as shown in the effect of heuristics. So this is generally happening to tell what I have told currently. So next we will talk about the model. So given the context and region, our next goal is to synthesize the color and depth values. So we have synthesized the context and all those layer stuffs. Now we will approximate the color and depth values of those regions. So here where the GAN part comes in with the unit. So even though we perform the synthesis on an LDI, the extracted context and the synthesis regions are locally like images. So we can use standard network architecture designed for images. So I will be using UNet. I will be showing the example of UNet, which they have cited in the inpainting paper. So we will go to that. So straightforward and naive approach is to inpaint the color image and the depth map independently. So as I said, using the Markov beef networks and all the stuff, we can just inpaint the color image and the depth map independently. The inpainted depth map, however, may not be well aligned with respect to the inpainted colors. Yeah, this is always a problem when we have a single image. So to address the issue, we will break down the architecture into 3 parts. That is edge inpainting network, color inpainting network, and depth inpainting network. So a model is having another 3 models within itself, and they're assembling the 3 models and creating a new model with that. So these are the dependencies which we will see. And any kind of, suppose we are having a problem in this model, so this will also be affected in the future of the model of of the model of this inpainting model. So a dependency issue will be there if the prior work is having some issues. So the new work will also have some issues if they have not improved on the prior works. But these guys have improved on the prior work, so that won't be much of an issue. So given the context as input, we use the edge inpainting network to predict the depth edges as synthesis network, producing the inpainting edges. So as I have told, so they are using the context as input, and from that we are using the edge inpainting network. So performing the steps first helps infer the structure in terms of depth edges that can be used for constraining the content prediction, the color and depth values. So this is the model. See. So they are having a depth model, depth synthesis model, selecting a subproblem, they are selecting a depth, they're even using the edge for the GANs for inpainting these models. So this is kind of a pipeline of the model which they have used. So these are different kind of state-of-the-art models. Mind you, these are not older than 5 years. And they're also using these models to get an ensemble of models for creating a new model. So here they are using the context, color, and depth inpainting network, and they're using the depth. So mainly they focus on 2 models, which is creation of a depth network and creation of a context color network. So I will be coming those in those slides. So yeah, so we take the concatenated inpainted edges and context region as input and use the color inpainting angle. So after we have secured the layers, we can now inpaint this. So see, these are occluded regions, right? So we can inpaint this using the models from GAN, which uses an edge estimation. So from a single image, we can determine the edge. So this will be a good method for converting image to 3D image by use of GANs uh, with an additional information of edge. Because GAN uses, if some additional information is supplied to GAN, it performs much better. So Figure 7 shows an example of how the edge-guided inpainting is able to extend the depth structure accurately and alleviate the color or depth misalignment issues. So here you can see that the color and depth misalignment. So model might also get confused that this and this layer might be different. So in that case, they are converting a single layer and applying the depth in painting there. So in depth complex scenarios, applying our inpainting model model bonds is not sufficient, as we can still see the hole through the discontinuity created by the inpainting. So we can see here, see this is a hole. So this is called as T junctions. So what is happening is after applying of certain iteration, they will fill the hole. So since this is an iterative algorithm, this will inpaint the model iteratively. So hence we apply our model until no further inpainting depth images are generated. So they are having a cost functions. They have not mentioned it in briefly in the paper also. I am assuming that they are having a cost function which minimizes every time, and using that we can guess that how many much depth we need to invent. Okay. So so firstly they are creating different layers here. So this is multi-layer inpainting which is applied here. So here we are creating a different layers, and since every images have different context, different perspective, so there these have initial layers LDI
No, you
image
need to speed up a little
have
bit.
roles in it.
Uh,
Yeah, I'm speeding up.
and I
So
cannot
this
give you
this have
more than 8 minutes, so try to finish fast. And then the next team would be Shubhashish and Monojit. Are you ready?
but it will take
Yes,
at
Manoj.
least 20 minutes, I think.
But no, we don't have
Maharaj.
the time for the other presentation that I need to give
Okay,
40
okay,
minutes
okay,
of
okay,
your
okay.
time.
Yeah. Okay, okay,
I would
okay.
like to give you more.
So
I'm giving you
these are
almost twice the time, right?
okay.
Okay,
Yeah.
continue.
Okay, so this is, so they're splitting up the layers, then they're inpainting it iteratively, and we can see that it is filling the holes very well after each iteration. So we are the training data is generated through MS Coco dataset, which have 330K images, 1.5 million object instances, 80 classes, and 5 captions per images. The model can train on any given dataset with proper annotated data. So we create a depth map of synthetic dataset. So we are using the Coco dataset for creating a depth map of synthesis dataset. We apply a treated mega depth. So mega depth is another model. This is a mega depth model. This is a mega depth pipeline. I will come to the mega depth model next. So on Coco data, we are using the mega depth model on Coco data to obtain pseudogram truth values of depth maps. We randomly sample and place this context synthesis region and image of context. Thus, we obtain a ground truth with selected regions. So this is what we are doing is we are randomly sampling the context layer synthesis and we are placing it, and we are leaving it to the algorithm to synthesize and do their job. So we are converting to textured 3D texture mesh. We form the 3D texture mesh by integrating all the infinite depth and color values back into the original NDA. So using mesh representation for rendering allows us to quickly render novel views without the need for per view inference steps. So with the use of novel methods like that, mega depth and all, we can use inference, and less computation is required. So consequently, the 3D depth estimation produced by our algorithms can be easily rendered using standard graphics engines and data. Experimental results. So these are these are the experimental results. So implementation details is they are using the Adam optimization. So Adam optimization is a mixture of Ada delta and Adam optimization is a mixture of Ada delta and another optimization method which have hyperparameters of 0.9. We can you can refer this for machine learning interested peoples. So we can train both the age and depth generator model using context synthesis region for 5 people. So in painting the model architecture for age in painting network, we follow the architecture of Edge Connect. So this is another method. So for in painting, they're using Edge Connect. So this is a GAN method, and for color in painting, they're using unit architecture. So this is the Edge Connect. So that method which I was talking about, this GAN can fill holes and all do all sort of creative stuff. So they're approximating edge map using this, and they are using synthesizes and filling the holes. So what can it do? The Edge Connect. So it can fill the holes. It can remove objects even. So we are creating a hole and synthesizing this, and it can also merge two images. So these are all the creative tasks this can be done by that. And this is the implementation details of the UNET paper. So this is also a recent paper. So it is the first paper having a deconvolution, which is very computationally efficient. So it is a convolutional networks for biomedical image segmentation. The architecture is shown here.
Unit you can
You
skip
can
because
apply
unit will be covered
deconvolution
by
to
the
create.
next presenter.
Yeah. So this is the architecture. This is the architecture of unit, and So we are using another DPS model. So this DPS model creates the depth map of that. So DPS model have this kind of depth map. It is very means very state of the art with all those filters. So this pipeline, and what we can see is these are the challenging example, and our methods performs better than the other methods. But there are also some shortcomings. So we can see that it is not very good in performing this synthesis of the region. So we are comparing this MPI. So I'm skipping this. These are very detailed explanations. So to give an overview of this, it performs better than the Facebook 3D models. So in this case, we can see a comparison of Facebook models. So this is Facebook's. It has creating a ghosting effect, and this is our model, which is good. So this is also having to apply good in other data sets as well. So this is input this megadata and this midas and kinetics. So our results on custom input. So this is the custom input. So firstly, what it does is it creates a zooming effect. So it creates 4 parts. So firstly, this is the zoom effect. So it is like creating a tree structure. It's not visible so much. Then it creates another variant using the circle effect. So what does this circle effect do? Is it kind of gives you a sense that the layers are not moving so fast. So with a single image, it is very good. So all in one, we are
Your voice is
applying
breaking a lot. Okay, and another thing.
issues.
Yeah. Continue.
So this is all in one swing. So this is another image. So we will see that we will. Okay, I am skipping this. This is zoom in. It is similar to that, and I will just give you the final result. So this is the swing. So what does swing does is it combines all the methods. It is just punching the first that is zoom in, dolly in and stuff. We are selecting a person and zooming it, and we are applying the swing method. So this is another image. So this is I'm skipping the swing and going to the final. So what it does, the swinging does is, wait a second. So this is swing. So what we can see that the earlier is not moving so much better with this, and this is a picture of a picture. So it also surprised me that it is very is performing very good in picture of a picture. So we can recreate the old memories using this. So this is quite good, and we can see that these have created different layers, and my head is moving faster than the previous years. So all this stuff, and this is a picture of Edwin Aldrin. So this is the depth map by meta depth. I will skip the. I will go to directly go to the actual swing method. So swing is again the combination of all those methods. So this is a very moon of this is second moon. I don't know. There are very controversies in this paper, in this image, if you know. So this is another. This is a picture of a duck. This is Sinsin. Sinsin is another method. So our method is state of the art and surpasses all these methods. So this is Kenburn's method. I have city Simpsons because it just does a pretty bad job in just zooming. So this is Kenburn's method. So we can see that there is a host like the Facebook method, and this is our method. So what our method does is it creates a context over 3D immersion. So we can say is immersion and also hosting effects have reduced quite significantly. So I will not go to the FB algorithm because you know that it's not so good, but we can see this our algorithm because we will see that it is performing better by having seen this. So scope for improvement. So this is another scope. So this is a still chart. So scope for improvement is in some cases it may also happen to the GANs are not working properly. So in that case, what it happens is layers are not created properly. So we can improve it. So see, we can say there is very distorted. These are very bad, and in this case, there is very scope for improvement. So this is a picture of my graduation, and there is also scope for improvement in this kind of pictures because you can see that they are not able to classify which segment belongs to which part. So my head is moving away. So all these stuff. So conclusion, in this investigation, we present an algorithm for creating a compelling 3D photography from a single RGBD image. Our core technical novelty lies in creating a complete layer depth image representation to context our color and depth in painting. We validate our method on a wide variety of everyday scenes. Our experimental results shows that our algorithm produces considerably fewer visual effects when compared with the state of the art. Yeah, so our algorithm is superior in general. So this can create a very good immersive. So these are the papers. So this is the paper which I have cited, which I have written based on. This is the paper for unit. This is the paper for Edge Connect. This is the paper for DSPNet, and this is my paper, which Tamal Maharaj for the. This have got something like the kernel methods and all the stuffs. So thank you.
Very good, Jimut.
Well done.
Yes, good. Very good job.
I know I have a like a little bit issues with time management.
Right, no, you have done actually very good job, and
Yeah.
I would like to give you more time because the in depth you go, the better it is for everyone to understand these papers. Because and all everyone also can understand that how much effort it needs to give a good presentation. Jimud already actually shared these slides with me, and I liked this very much. So I thought I'll give him a chance first, so that others can be motivated, like what sort of presentation they should make. At least the effort he has put, that is commendable. And Jimod, you can also share these slides with everyone along with giving access to the video.
Yeah. I will share it.
Make sure that you give
Yeah. I will
videos.
share. Yeah.
The videos
Yeah.
still I could.
But actually, I have asthma, so I have asthma, so I have a little problem in conversing means very fast. So
Oh, okay. Sorry
it's
about that.
means I know it compromise some of the voice and all this.
Yes. And we would like to hear more, but at least you share the slides with everyone so everyone can watch the videos, whatever you have done. But I have one question. Uh, the photos you have taken, is the depth information available there?
No. In my cases, which I have taken is using a single camera. Depth
Right.
information is not available. Some alpha value may be available, but it is just RGB image. So this is the crux of the algorithm. What they are trying to improve is using a simple image. Using some simple image, we can implement this using in Android devices for
Mhm.
for noobs who are not having means like noobs like us. We are not having access to all this calibration and all this accuracy for taking the two or more image with highly sensitive depth map. So we are kind of like, this is kind of giving away some free technologies to general public. So this is
Right,
quite
but
improvement
in
on this one.
Jimu, in the real paper, they have worked with the 3D, like the images which has got depth. Is that correct?
Yeah, exactly. So in that case they have performed they have gotten a better result than me. But in my case also, we can see that flower image which I showed you, it doesn't have depth value, but it works well because they are using a pretend model, using that I talked about H connect. So it is kind of creating a depth value from itself. It is approximating. And
Mhm.
you have also shared your slide, the last slide which you shared in Google's Classroom. That also have some papers related to GANs which are able to extract the depth information with pretend transfer learning. So they are using all the stuffs, recent stuffs. So it's
Right.
very
So you
quite
can
good.
actually, I'm not asking you right to do right now, but later you can try to do that. Like if you just do draw the depth map of the non-depth image that you have, how does it
Yeah.
perform? Just
So
you can experiment that, and it can be a wonderful algorithm or thing to do. Like if you have an image
exactly.
without the
I want
depth, how
I
can
want
you
I want to.
still can get the depth information? Sometime you can probably draw some lines to mark, okay, this is the foreground and that is the background, and if you give that information, how still you can draw the image? Getting that kind of.
Exactly. Yeah, exactly.
So this is a
And
very
it may
good
also happen
actually.
that it may also happen that in future we are having several more data set. So this data hungry algorithms can take all those more data set to create a general intuition of how to separate the depth map. So in future it may also improve tremendously.
Okay, so we'll talk about that later.